In this unit, we're going to talk about titrations. Now, in an acid-base titration, a solution of unknown concentration called the titrant is slowly added to a solution of known concentration from a burette until the reaction is complete. And when the reaction is complete, we have reached the end point of the titration. An indicator may be added to determine the end point, which is a chemical that changes color when the pH changes. So when the moles of acid equals the moles of base, the titration has reached its equivalence point.
Initially, you may add the titrant rapidly while swirling the Erlenmeyer flask. The indicator will begin to change color in regions of high titrant concentration, but with swirling, the color will disappear before the equivalence point is reached. Slow down the titration when the color change becomes more pervasive and begins to linger throughout the flask. Add the titrant dropwise at the end. At the very end of the titration, you can add a split drop by touching a hanging drop of titrant on the nozzle to a stirring rod, then stirring it into the solution. You are looking for the one drop or split drop that causes the color to change for at least 10 to 15 seconds.
Now, before we begin, let's talk about a way to simplify the calculations we'll be making. Molarity, you all know, is moles of solute per liter of solution, but it can also be expressed as millimoles per milliliter. A millimole is 1,000th of a mole. A milliliter is 1,000th of a liter. So molarity can also be expressed as millimoles per milliliter. This simplifies calculations because we don't have to convert continuously into liters. If I have molarity expressed as millimoles per milliliter and I multiply by milliliters, I get millimoles. If I have millimoles and I divide them by milliliters, I end up with molarity. So multiplying molarity by milliliters gives millimoles. Dividing millimoles by milliliters gives molarity. So now let's talk about titrating 25 milliliters of 0.1 molar hydrogen chloride with 0.1 molar sodium hydroxide and plotting the pH versus the amount of sodium hydroxide that we use, we get something called a titration curve. So before I start the titration, I just have 0.1 molar HCl, and if I take the negative log of 0.1, I get a pH of exactly 1. So that's right here. Now I start to add sodium hydroxide. And as I add sodium hydroxide, the pH slowly increases until we get near the equivalence point. The equivalence point is when I add equal number of moles of hydroxide as I have moles of hydrochloric acid. And at that point, the pH very quickly changes. So the second calculation is the addition of hydroxide until just before the equivalence point. The third determination would be the pH right smack at the equivalence point. And if we're dealing with a strong acid against a strong base like we are here, that equivalence point is going to have a pH of 7. We don't even have to worry about doing a calculation there, because we know when hydronium ion equals hydroxide ion, the pH is 7. The last calculation is when we go beyond the equivalence point, and now we are definitely in basic territory with a pH greater than 7. So this is the last calculation we need to make, what the pH will be after the equivalence point. So now let's try to do this. Turn your playback off. Try and do this calculation. You should be able to at this point. Come up with the pH after we mix 25 milliliters of 0.2 molar HCl with 20 milliliters of 0.15 molar sodium hydroxide. Playback off, try it, and then come back. We'll discuss it. All right, here's our reaction. Hydronium plus hydroxide yields 2 moles of water. We'll find the millimoles of hydronium ion, that's 25 milliliters times 0.2 millimoles per milliliter of HCl. So that'll be 5 millimoles of hydronium ion, and 20 milliliters times 0.15 molar sodium hydroxide is 3 millimoles of hydroxide. So we have 5 millimoles of hydronium, 3 millimoles of hydroxide. Of the 5 millimoles, 3 millimoles of hydronium ion will react with and be neutralized by the hydroxide, leaving behind 2 millimoles of hydronium ion and 0 millimoles of hydroxide. So we know we have 2 millimoles of hydronium ion in a total of 45 milliliters of solution. That's 25 milliliters from the acid mixed together with 20 milliliters from the base. So 2 millimoles divided by 45 milliliters is 0.044 molar hydronium ion. Converting that with the negative logarithm into pH, we get a pH of 1.35. Now how about this question? What is the pH of a buffer that has 0.1 moles of acetic acid and 0.1 moles of conjugate base, that's the acetate ion, in 1 liter, and to that 0.01 moles of sodium hydroxide is added? What will be the pH after you mix in the sodium hydroxide? And here are some hints to help you do the calculation. First, calculate the new concentration of acetic acid and acetate ion after the hydroxide is neutralized by the acetic acid. This is a one-way reaction. It is not an equilibrium. Like this. So initially we have 0.1 moles of acetic acid, 0.01 moles of hydroxide that we've added in, and 0.1 moles of the acetate ion. Now what's going to react? 0.01 moles of the acetic acid is going to react with the hydroxide and form 0.01 moles of the acetate ion. After this reaction, it means that we have 0.09 moles of the acetic acid left over. We've neutralized all the hydroxide, and we've formed a little bit more of the acetate ion, 0.11 moles. So now use these new concentrations of weak acid and base, and the Ka for acetic acid, 1.8 times 10 to the minus 5, to calculate the pH. Turn your playback off, do the calculation, and then come back and check. All right, so here we go. This is the equilibrium that we're interested in. Acetic acid plus water yields the acetate ion plus hydronium ion. And our mass action equation, of course, looks like this. So now we simply plug in the acetate ion, 0.11 molar, and in the denominator we put our acetic acid concentration, 0.09 molar. We solve for hydronium ion, 1.47 times 10 to the minus 5, and calculate the pH from that, 4.83. Well, what was the pH before hydroxide was added? Well, if we plug the acetic acid concentration into the mass action equation along with the conjugate base, they're both 0.1 molar, and they both cancel out, leaving hydronium ion equal to the equilibrium constant, 1.8 times 10 to the minus 5. Taking the negative log of that, we get a pH of 4.74. So comparing, after we add hydroxide, we see a very slight change in pH to 4.83. The pH was 4.74 before we added hydroxide. That's a good example of what a buffer does. It prevents a rapid change in pH. Now let's take a look at the titration of 25 milliliters of 0.1 molar weak acid with 0.1 molar sodium hydroxide. And we're given the equilibrium constant for this weak acid as 1.8 times 10 to the minus 4. Before we add any hydroxide, we have the first type of calculation to do, which is simply finding the pH of 0.1 molar weak acid. The next type of calculation is when we begin to add the hydroxide. In this kind of calculation, we really have two steps. The first is to neutralize a portion of the weak acid with the hydroxide, forming some conjugate base, and then run the calculation based on the amounts of weak acid and conjugate base that we have. So there are really two steps there. First, the neutralization step, and then calculating the pH based on the amount of weak acid and conjugate base. We should note the point of most efficient buffering where 1/2 of the weak acid has been neutralized. So we have equal amounts of weak acid and its conjugate base. At that point, pH equals the pKa of the weak acid. The third type of calculation occurs right at the equivalence point. where we have neutralized all of the weak acid. So we just have its conjugate base present in water, and we run the calculation based on that amount of conjugate base. And the last type of calculation is if we continue adding hydroxide to this solution, and all we need to do is calculate the molarity of hydroxide based on that excess and calculate a pH from that. The excess hydroxide is the proverbial 300-pound gorilla in the room. That is to say, the amount of hydroxide generated from weak base is minuscule compared to the excess hydroxide that we've added. So we can ignore the equilibrium calculations based on conjugate base. Okay, let's do the first calculation. Before we add any sodium hydroxide, what is going to be the pH of 0.3 molar weak acid? So do the calculation, put your playback on pause, and come back and check. All right, so we have a weak acid ionizing in water, forming hydronium ion and acetate ion. And at equilibrium, we have 0.3 minus X, which is just about equal to 0.3 for the weak acid concentration because Ka is such a small number. Plugging in X in the mass action equation, X will equal hydronium ion and X will equal conjugate base. So that'll be X squared in the numerator. In the denominator is the concentration of weak acid, which is going to be 0.3 molar with the approximation. Solving for X, we get 9.2 times 10 to the minus 4. Or the pH is going to be 3.04. Our second calculation, we have to determine the milliliters of 0.1 molar sodium hydroxide to add to get to the point of most efficient buffering. Do the calculation after you turn your playback off and then come back and check your work. Okay, here we go. The most efficient buffering occurs when 1/2 of the weak acid is converted to conjugate base. So we have 7.5 millimoles of weak acid. We get that by multiplying 25 milliliters times 0.3 molar. We get 7.5 millimoles of weak acid. 1/2 of that number is 3.75 millimoles of hydroxide to add to get 3.75 millimoles of conjugate base. This is a one-way reaction where the weak acid reacts with hydroxide to form the conjugate base A- and water. This is not an equilibrium. So here's the calculation. 1/2 of 0.3 times 25 is 3.75 millimoles of HA. It's neutralized to yield 3.75 millimoles of A- and 3.75 millimoles of HA are left over. So A- concentration equals HA, weak acid concentration, and they therefore cancel each other out in the mass action equation, leaving the concentration of hydronium ion equal to the equilibrium constant for the weak acid. So at the point of most efficient buffering, the concentration of hydronium equals equilibrium constant, and the pH equals the pKa. So now the question is, how many milliliters of 0.1 molar sodium hydroxide, which is, after all, 0.1 millimoles of sodium hydroxide per milliliter, contains 3.75 millimoles of hydroxide, because that's what we need to neutralize 1/2 of the weak acid. Multiplying 3.75 millimoles by our ratio inverted with 1 milliliter in the numerator and 0.1 millimoles of sodium hydroxide in the denominator, we get 37.5 milliliters. And that's the answer. Okay, here's our next question. What is the pH after 45 milliliters of 0.1 molar sodium hydroxide is added? Turn your playback off, try the calculation, and come back and check your work. Okay, here we go. First, find the new concentrations of weak acid and conjugate base using this one-way reaction. The weak acid plus hydroxide yields conjugate base plus water. So for the weak acid, we start off with 25 milliliters of 0.3 molar weak acid, or 7.5 millimoles of weak acid. To that, we add 45 milliliters of 0.1 molar sodium hydroxide, which is 4.5 millimoles of hydroxide. we have excess weak acid to react with the hydroxide. Of the 7.5 that we start with of the weak acid, 4.5 millimoles of weak acid is going to react with the 4.5 millimoles of hydroxide to leave behind 3 millimoles of weak acid in 45 milliliters plus 25 milliliters, a total of 70 milliliters of solution. So the new concentration of weak acid is 3 millimoles of weak acid divided by 70 milliliters, or 0.0429 molar in weak acid. And the conjugate base A minus, we have 4.5 millimoles, which formed from the reaction of hydroxide with weak acid in 70 milliliters of solution. So the concentration of conjugate base is 4.5 millimoles divided by 70 milliliters, or 0.0643 molar conjugate base. Plugging these values into the mass action equation and solving for hydronium ion, we get 1.8 times 10 to the minus 6 as the concentration of hydronium ion. And taking the negative log of that, we get a pH of 5.73. Okay, our next question, what is the pH after 75 milliliters of 0.1 molar sodium hydroxide has been added? Do the calculation and come back and check your work. Here we go. 0.1 molar hydroxide ion is 0.1 millimoles of hydroxide per milliliter times 75 milliliters. We've added 7.5 millimoles of hydroxide to this solution, and we have 0.3 molar weak acid times 25 milliliters is also 7.5 millimoles of weak acid. So now this is the equivalence point, and all of the weak acid reacts and is converted to 7.5 millimoles of conjugate base in this one-way reaction. We now have formed 7.5 millimoles of conjugate base in a total volume of 100 milliliters of solution, and therefore the concentration of conjugate base is 0.075 molar. Now we can look at the equilibrium reaction of a weak base in water. Conjugate base A minus plus water yields weak acid plus hydroxide ion. So at equilibrium, we have X for the conjugate acid, X for hydroxide ion, and 0.075 minus X, which is just about equal to 0.075 for conjugate base A minus. We need to calculate the equilibrium constant for this weak base, and we do that from the equilibrium constant of the weak acid, Ka. Kb is equal to 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 6. So the Kb is 3.57 times 10 to the minus 9. Plugging into the mass action equation, we get x squared divided by 0.075 is equal to 3.57 times 10 to the minus 9. Working that out, we get x equal to hydroxide ion concentration of 1.6 times 10 to the minus 5. Remember, this is hydroxide, not hydronium ion. So the pOH is the negative log of that number, 4.79, and we want the pH, 14 minus 4.79, which is a pH of 9.21. That's the pH at the equivalence point. So here's our last question in this series. What is the pH after 85 milliliters of 0.1 molar sodium hydroxide has been added? Do the calculation, come back, and we'll discuss it. All right, here we go. We're going to take 0.1 millimoles of sodium hydroxide per milliliter, multiply it by 85 milliliters. We get 8.5 millimoles of hydroxide, and that's added to 7.5 millimoles of the weak acid. So 7.5 millimoles of the hydroxide will neutralize the weak acid, forming 7.5 millimoles of A minus, and it leaves behind an excess of 1 millimole of the hydroxide ion, which, like the 800-pound gorilla, completely dominates the pH. We can ignore the reaction of conjugate base with water and just calculate the pH based on this excess 1 millimole of hydroxide, dissolved now in a total volume of 110 milliliters of solution. So 1 millimole of hydroxide divided by 110 milliliters is 9.09 times 10 to the minus 3 molar in hydroxide, not hydronium, hydroxide. So the pOH is the negative log of that number, which is 2.04. And now the pH is therefore going to be equal to 14 minus 2.04, or 11.96. Now let's talk about buffering effectiveness. A good buffer should be able to neutralize moderate amounts of added acid or base. However, there's a limit to how much can be added before the pH changes significantly. The buffering capacity is the amount of acid or base a buffer can neutralize, and the buffering range is the pH range in which the buffer can be effective. The effectiveness of a buffer depends on two factors. First, the relative amounts of weak acid and conjugate base, and second, the absolute concentrations of weak acid and base. Let's look at buffering capacity first. The buffering capacity is the amount of acid or base that can be added to a buffer without destroying its effectiveness. The buffering capacity increases with increasing absolute concentration of the buffer components. The more concentrated a solution is in the buffering components, the more buffering capacity for that buffer. As the base to acid ratio approaches 1, the ability of the buffer to neutralize both added acid and base improves. Buffers that need to work mainly with added acid generally have the weak base component at a concentration greater than the weak acid component, and buffers that need to work mainly with added base generally have the weak acid component greater than the weak base component. Now let's do some calculations to show how the ratio of buffer components affect the effectiveness of the buffer. In our first example, in buffer 1, we have a 1-to-1 mole ratio of weak acid to conjugate base, 0.01 moles each, with an initial pH of 5.0. In buffer 2, I have much more of the weak acid, 0.18 moles of weak acid, and only 0.02 moles of conjugate base. So I'm going to add to buffer 1 0.01 moles of hydroxide, and it changes the weak acid concentration from 0.1 to 0.09. Meanwhile, the conjugate base concentration grows by 0.01 from 0.10 to 0.11. We plug those into the Henderson-Hasselbalch equation, and we get a pH calculated as 5.09. Now I'm going to do exactly the same thing where we don't have a 1-to-1 ratio, where I have much more of the weak acid than conjugate base. I'm still going to add 0.01 moles of hydroxide to the system, and the weak acid drops from 0.18 to 0.17. The conjugate base grows from 0.02 to 0.03. I run that into the Henderson equation. I get a pH of 4.25. So there are my new pH values. The percent change for buffer 1 is 5.09 minus 5 divided by 5 times 100%, or a change of 1.8%. In buffer 2, the change is 4.25 minus 4.05 divided by 4.05 times 100%, or a 5% change. A buffer is most effective with equal concentrations of weak acid and conjugate base. Buffer 1 has protected the system from pH change much better than in buffer 2. Now let's look at the effect of absolute concentrations of weak acid and conjugate base to the effectiveness of a buffer. In buffer 1, we have 0.5 moles of weak acid and 0.5 moles of conjugate base. In buffer 2, we have buffer components at 1/10 the concentrations of buffer 1, at 0.05 moles of weak acid and 0.05 moles of conjugate base. The initial pH in both is 5. Now let's add a strong base to each one of these buffers and see which one protects against pH change. In buffer 1, we add 0.01 moles of hydroxide. The weak acid becomes 0.49 moles. The weak base becomes 0.51 moles. Plugging those into the Henderson equation, I get a pH of 5.02. Now I do the same thing to buffer 2, adding 0.01 moles of hydroxide. The weak acid drops from 0.05 to 0.04. The conjugate base is increased from 0.05 to 0.06. Running that through the Henderson equation, I get a pH of 5.18. So here are the two pH changes, and if I calculate the percent change in each one, I get a percent change of 0.4% for buffer 1 and a percent change of 3.6% for buffer 2. Buffer 1 with higher concentrations of weak acid and conjugate base is much more effective at minimizing the change in pH. So for the effectiveness of buffers, a buffer will be most effective when the concentration of weak base to weak acid is 1. In other words, we have equal concentrations of weak acid and its conjugate base. And it is at this point that pH equals pKa. A buffer is effective when the weak base to weak acid concentration ratio is between 0.1 and 10. Therefore, the effective pH range of a buffer is with a pKa of plus or minus 1. So, when choosing an acid to make a buffer, choose one whose pKa is closest to the pH of the buffer. Now let's do a practice problem similar to the one we just did to see if you've gotten the hang of it. A 40 milliliter sample of 0.1 molar nitrous acid is titrated with 0.2 molar potassium hydroxide. And the first part of this, calculate the volume of potassium hydroxide at the equivalence point. Turn your playback off, try to do it, and come back and we'll discuss it. Well, at the equivalence point, you add an equal number of moles of hydroxide as you have moles, or millimoles, of nitrous acid. So, first you determine the millimoles of nitrous acid by multiplying the volume of the nitrous acid by its molarity, and that gives you 4 millimoles of nitrous acid that need to be completely neutralized. So at the equivalence point, we add an equal number, 4 millimoles of hydroxide. And to get the number of milliliters of hydroxide solution, we multiplied the desired millimoles of potassium hydroxide by the inverted molarity so that millimoles cancels out and leaves our answer with the units of milliliters. And the answer is 20 milliliters. So for the next question in this series, calculate the volume of potassium hydroxide to add that would result in the most effective nitric acid nitrite ion buffer possible. Turn your playback off, try it, and then come back and check your answer. So here we go. At the point of most effective buffering, nitrous acid concentration equals the nitrite ion concentration, the conjugate base. So we need to convert 1/2 of the millimoles of nitrous acid, which would end up being 2 millimoles, 1/2 of 4 millimoles, 2 millimoles, into nitrite ion. So how many millimoles of 0.2 molar potassium hydroxide will contain 2 millimoles of hydroxide? Because 2 millimoles of hydroxide will react with 4 millimoles of nitrous acid to neutralize 1/2 of the nitrous acid, so that we end up with equal concentrations of nitrous acid and nitrite ion. So all we do is multiply 2 millimoles of hydroxide by the inverted molarity, milliliters in the numerator, 0.2 millimoles in the denominator, to give an answer of 10 milliliters. So in the last question of the series, if the equilibrium constant for our equilibrium of nitrous acid and nitrite ion is 4.6 times 10 to the minus 4, calculate the pH of the point of most effective buffering. Try it, turn your playback off, then come back and we'll discuss it. So at the point of most effective buffering, the concentration of nitrous acid equals the concentration of the nitrite ion, its conjugate base. For the equilibrium of nitrous acid ionizing in water to form the nitrite ion and hydronium ion. So we have this mass action equation from this equilibrium. And at the point of most effective buffering, the concentrations of nitrous acid and nitrite ion are equal. so they cancel out, leaving the concentration of hydronium ion equal to the equilibrium constant for this weak acid, 4.6 times 10 to the minus 4. And therefore, the pH will equal the pKa at this point of most effective buffering. So, with pH equaling pKa, therefore, if we simply find the pKa of 4.6 times 10 to the minus 4, that will be equal to 3.34. That's the pKa, but it's also the pH at the point of most effective buffering. Which of the following acids would be the best choice to combine with its sodium salt, its conjugate base, to make a buffer with a pH of 4.25? Think about these choices, make a decision, and then come back and we'll discuss it. All right, if we think about the Henderson-Hasselbalch equation, where pH equals pKa plus the log of, well, you know the ratio, right? We know that the most effective buffering occurs when the concentration of conjugate base equals the concentration of weak acid. In other words, when this ratio is 1. And at that point, the log of 1 is 0. Therefore, at the point of most effective buffering, and you know this already, pH equals pKa. Therefore, you would want to choose a weak acid whose pKa is as close as possible to the pH of the buffer that you're trying to make. So for this question, our target pH for the buffer is 4.25, and the pH closest to that of all the four listed here is C, formic acid, at 3.74. Okay, which line below provides two substances when mixed together in water that would provide a buffer solution? Turn your playback off, think about it, choose an answer, and we'll come back and discuss it. So if you chose line A, that's not going to be it because HCl is a strong acid, and to have a buffer, you need a weak acid together with its conjugate base. So it can't be A, nor can it be B because you still got a strong acid present. C looks promising at the beginning because you got ammonia, and if you had some ammonium ion, its conjugate acid, that would be a buffer mix. But you don't. You have it mixed with another base, sodium hydroxide. And the last one, E, perchloric acid, is one of the strongest acids known, and that certainly is not going to provide a buffer. So answer D, acetic acid is a weak acid, and sodium acetate is its conjugate base, and it's good for a buffer. Now, of course, you know we can make a buffer system out of a weak base and its conjugate acid. So let's try doing the calculations in a system like that. Here we're titrating 25 milliliters of 0.1 molar ammonia with a Kb of 1.8 times 10 to the minus 5 with 0.1 molar hydrochloric acid. The first question, what is the pH before any hydrochloric acid solution is added? Go ahead and try it and then come back and we'll discuss it. All right, so here we are. Here's ammonia plus water yields ammonium ion plus hydroxide ion. Initially we have 0.1 molar of ammonia, and before any ionization we have no ammonium ion nor hydroxide. So of the ammonia, minus X molar ionizes to form X molar of ammonium and X molar of hydroxide. We make the approximation, 0.1 minus X is just about equal to 0.1 because the Kb is such a small number. And we set up our mass action equation to equal the Kb. X squared over 0.1 equals 1.8 times 10 to the minus 5. So X equals 1.34 times 10 to the minus 3, which is the concentration of ammonium ion and the concentration of hydroxide ion. So the pOH is the negative log of this number, which comes out to be 2.87. And of course, the question is asking for pH. Therefore, we have to take 14 minus 2.87 to get a pH of 11.13. So now let's calculate the pH after 12.5 milliliters of 0.1 molar hydrochloric acid is added to 25 milliliters of 0.1 molar ammonia. Do the calculation and then come back and we'll discuss it. Well, first we find the millimoles of the ammonia. We get 2.5 millimoles of ammonia, and 12.5 milliliters times 0.1 molar HCl equals 1.25 millimoles of HCl. We have a one-way reaction to do first before we think of an equilibrium, because the ammonia is going to react with the HCl in a one-way reaction, not an equilibrium, to form ammonium ion and chloride ion. And doing the calculations to see what we have left after the reaction, we see that 1/2 of the ammonia is neutralized, and we have 1.25 molar of the ammonia left over and 1.25 of the ammonium ion being formed. Therefore, at equilibrium, we have ammonia plus water yields ammonium ion plus hydroxide. We set it up in a mass action equation to equal 1.8 times 10 to the minus 5. And we plug in our weak base ammonia and conjugate acid ammonium ion, which of course cancel out, leaving us with a concentration of hydroxide equal to 1.8 times 10 to the minus 5, equal to the Kb. pOH, therefore, is going to be 4.74, and subtracting that from 14, we get 9.26. Now let's do the calculation to find out what the pH is after 25 milliliters of 0.1 molar HCl is added, the same number of millimoles as we have millimoles of ammonia. Turn your playback off, try it, and come back. We'll discuss it. So as I noted, we have 2.5 millimoles of ammonia and 2.5 millimoles of HCl, which means all the ammonia is going to be neutralized. And therefore, we need to figure out what the pH is going to be at the equivalence point. Now, at the equivalence point, we have 2.5 millimoles of ammonium ion that was formed in the neutralization, and a total of 50 milliliters of solution, 25 and 25. That gives us a molarity of 0.05 molar for the ammonium ion. Plugging that into our mass action equation for the reaction of ammonium ion with water forming ammonia and hydronium ion, we have this mass action equation equaling the Ka for ammonium ion. Now we can calculate what the Ka for ammonium ion is going to be, because Ka times Kb has to equal 1 times 10 to the minus 14. So the Ka has to equal 1 times 10 to the minus 14 divided by ammonia's Kb. So that's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. 5.56 times 10 to the minus 10, that's the Ka for ammonium ion, acting as an acid. Setting up the mass action equation and plugging in, we have x squared divided by 0.05, remember we calculated that up here, equal 5.56 times 10 to the minus 10. We've solved for x, that's the hydronium ion, we get 5.3 times 10 to the minus 6, and we convert that into pH with the negative logarithm, we get a pH of 5.28. And finally, what's the pH going to be after 28 milliliters of 0.1 molar HCl is added? Turn your playback off, try the calculation, and come back. We'll discuss it. So now we have an excess of HCl that we've added, right? We've got 2.5 millimoles of ammonia, but 28 times 0.1 molar HCl is 2.8 millimoles of HCl. So the HCl is going to neutralize all of the ammonia and then completely dominate the pH. It's the 800-pound gorilla after all. And the acidity caused by ammonium ion is negligible compared to the excess of HCl that we have floating around in there. So we take our 0.3 millimole excess and divide it by the total volume that we have, 25 plus 28, which is 53 milliliters. And we get a molarity of HCl, or hydronium ion, of 5.66 times 10 to the minus 3. Simply to find the pH, we take the negative log of 5.66 times 10 to the minus 3, and we get 2.25. Now let's talk about indicators. Many dyes change color depending on the pH of the solution, and these dyes are weak acids, establishing an equilibrium with water and the hydronium ion in the solution. So here's our equilibrium expression for the indicator in the weak acid form, and then the indicator in the conjugate base form. And these two have different colors. The color of the solution depends on the relative concentrations of the indicator in the conjugate base form and the indicator in the conjugate acid form. When both of these forms are about equal, the color will be a mix of the colors of the weak base and the conjugate acid of the indicator. So here's a list of various acid-base indicators and their colors, both in the acid form and in the base form. And you can see there's quite a range of them. So if I ask you a question like this, a weak acid is titrated with a strong base, at the equivalence point the pH is 8.57, so which indicator below would be best to use to indicate that you have reached the equivalence point? And your 5 choices are thymol blue, brom cresol green, brom cresol purple, metanitrophenol, and thymolphthalene. So which one would you choose? If we look at the desired pH, 8.57, there's really only one that has a color change right around 8.57, and that would be the thymol blue, the very first one. So that's the indicator that you'd use.